Hello everyone, I welcome you all to the course UAV Design. Today we're going to discuss about Autopilot Compartment. The term compartment might suggest a simple physical box. It encompasses the sophisticated electronic intelligence and control systems that enable unmanned aircraft to fly. So basically, it's a compartment where we'll have the sensors, which is completely dependent on electronics, right? Which will be able to fly our unmanned air vehicle. In essence, it's the brain of the unmanned air vehicle, replacing the human air screw and their intricate interfaces. What is the Automatic Flight Control System, AFCS? At the core of the autopilot compartment is the Automatic Flight Control System, or AFCS. This system is the thinking part of the unmanned air vehicle, responsible for controlling and stabilizing the aircraft during the flight. The AFCS accepts commands, compares the aircraft's current orientation and state with the commandant parameters, and then issues instruction to other parts of the system to make necessary corrections. Autopilot role in control versus stability. Control refers to the means of directing the aircraft into its required position, orientation, and velocity. For example, changing the direction or speed of the unmanned air vehicle. Stability is the system's ability to maintain the aircraft in those desired states, ensuring it does not wander off course due to external influences like turbulence and gust loads. The sudden disturbances, ensuring that sudden disturbances are not destabilizing the unmanned air vehicle. Autopilot compartment role in automation versus autonomy. Automation, the AFCS provides automatic decision making where a pre-programmed flight profile or set of rules is executed without continuous human input. For instance, a UAV flying a pre-programmed mission from takeoff to landing without further external instructions is considered automated. Autonomy, a more advanced capability involving artificial intelligence, allowing the system to make its own decisions without human intervention or pre-programming in response to unplanned situations. This requires intelligence and a readily available source of experience. Components of the AFCS autopilot compartment. The autopilot compartment, more accurately, the electronics module or avionics bay, houses several critical subsystems. The first one, sensors. These are the eyes and ears of the AFCS. Category 1 under center sensors are attitude and heading sensors, in which it is subcategorized as vertical attitude gyros, which measures pitch and roll angles relative to the horizon. The second category is heading gyros and magnetometers, which are used to provide directional information of unmanned air vehicle. The third one in this category is angular rate gyros, which is used to measure rotation rates around the aircraft's axis, like pitch, roll, yaw, which is essential for damping oscillations. Strapped down systems. These are the modern systems often use these, where sensors are fixed to the aircraft body axis, directly providing body rates for control and relying on mathematical integration for attitude and heading. These are the axes. Longitudinally, it will nose goes up or down. If it is nose up, it is pitch up. Nose down is pitch down. Same thing if we see from the top view. This is yawing. If it moves to right side, it is a positive yawing movement. If it is moving to the left side, it is negative yawing movement. This is with respect to the longitudinal axis, this direction. And when it comes to roll, this comes into the picture. We'll see here. If this is moving up, this is coming like this, it is positive rolling movement, and if it is vice versa, it is negative rolling movement. Next, second category under this is height and altitude sensors, where we use radio altimeters, which are used to measure the tape height, which is the vertical distance above the ground. Barometric pressure and sensors, which measures pressure height, altitude above mean sea level. We have another category here, which will be housed inside this avionics compartment, is airspeed sensors, which will constitute of pitot static systems and integrated GPS system. Pitot static system is used to measure the standard for HTOL, that is horizontal takeoff and landing aircrafts, and integrated GPS system is preferred for VTOL, which is vertical takeoff and landing aircraft, due to PS system, pitot system inaccuracies. This PS is pitot system. Pitot systems inaccuracies at low speeds and variable airflow. Pitot static systems. Computing core, this is the brain of the system, processing all sensor data and executing flight programs. It contains memory to store mission plans, localized flight programs, and potential a database of flight characteristics. Modern AFCS logic is typical, digital, and software based. Actuators are used. These are the muscles that translate the AFCS commands into physical movements. They operate the engine controls, which is throttle, which we use to increase and decrease the thrust, and the aerodynamic control surface, for example, ailerons, which we control for rolling, elevators, which we control for pitch up and pitch down, rudders, which we use for moving right and left, that is yawing motion for fixed wing, and collective and cyclic pitch for rotary wing. Oftenly we use them which are electrically powered. Power supply systems. These are reliable electrical power, which is critical for all AFCS components, communications, and imaging systems. This can come from batteries or engine-driven alternators. The communication links, while a separate system, the AFCS interfaces directly with the communication system to receive control inputs and transmit data. Physical packaging and considerations. The removal of air screw and their accommodation allows for a much denser packaging of electronic and optical components, leading to a smaller and lighter aircraft. The electronics bay is often designed as a detachable module within the airframe, facilitating ease of build, maintenance, and replacement. Cooling for electronic components is a critical design consideration due to heat generation, especially in tightly packed spaces and hot ambient conditions. Electromagnetic compatibility is vital to prevent interference between electronic components, necessitating careful layout and shielding. The AFCS operates as an integral part of the total UAV system, where no single subsystem is more important than other, though the aircraft often drives the requirements for other elements. The control channels. The AFCS manages several key control channels. First one, speed channel, which compares commanded airspeed with actual airspeed and adjusts propulsor thrust accordingly. Heading channel compares commanded heading with actual heading and operates rudder and ailerons for correction. Height and altitude channel, it compares commanded height, altitude with sensed data, adjusting elevator deflection and propulsive thrust for climb or descent. Stability implementation using autopilot compartment. For aerodynamically stable aircraft, for example, traditional fixed wing, the AFCS provides damping and precise control, but the aircraft will still respond to air mass movements. For spatially stabilized aircraft, the airframe is designed to have minimal aerodynamic stability, for example, smaller control surfaces, zero wing dihedral, and the AFCS then provides the necessary spatial datum and stability using sensors like vertical attitude gyroscopes. Aircraft configuration specifies HTOL is horizontal takeoff landing fixed wing, uses aerodynamic control surfaces like ailerons, elevators, and rudders. Single main rotors are SMR helicopters. Control is complex, involving collective pitch for vertical lift, longitudinal cyclic pitch for forward-backward movement, and lateral cyclic pitch for sideways movement, rolling movement, plus a tail rotor for yaw control and torque counteraction. The AFCS must manage these complex couplings. Coaxial rotor helicopters offer great symmetry, simplifying the AFCS design due to fewer complex mode couplings. Yaw control, for instance, is achieved through differential collective pitch with no resulting side force to balance. Hybrid aircraft, for example, using tilt rotor mechanism, which can vertically take off and cruise horizontally. The AFCS is significantly more complicated as it must manage the transition between hover and cruise, phasing in and out different control mechanisms, for example, tilting rotor shafts and wing flaps. Payload control. The AFCS can integrate payload control, directing the sight line of sensors and enabling complex scanning maneuvers, or it can operate through a separate module that interfaces with AFCS for aircraft attitude data. Designing the autopilot compartment and its AFCS involves numerous challenges. First one is scale effects. Smaller UAVs operate at lower Reynolds numbers, leading to higher aerodynamic drag and lower achievable lift coefficients, which the AFCS must compensate for. Reliability. The AFCS is flight critical, robust design and rigorous testing, which is essential to meet reliability targets, especially given historical failure rates where power plant and flight controls are major contributors. Environmental resilience are the components which must withstand extreme temperatures, humidity, and vibrations experienced during transport, ground operations, and flight. Regulatory compliance. Meeting airworthiness and airspace usage requirements, particularly the detect, sense, and avoid mandate for operation in civilian airspace, which demands highly efficient and reliable sensing, and avoidance capabilities that may need to exceed human pilot performance. The autopilot compartment, or more accurately, the sophisticated automatic flight control system, is a linchpin of modern UAV operations. It integrates a complex array of sensors, computing power, and actuators to manage the aircraft's control and stability, adapting to diverse configurations and potential demands. The ongoing evolution of this technology, especially towards higher level of automation and autonomy, continues to shape the future capabilities and broader deployment of unmanned aircraft systems. These are the references used for the lecture. Thank you. We'll meet in the next lecture.